Hi everyone, in this lecture and the upcoming lectures, we'll be talking about window forensics. And if you guys are interested in further reading, you can refer to the Guide to Computer Forensics and Investigation, and it is chapter number 5 in the book. So the objective for this whole slide set is to understand the hard disk and their architecture. So we'll be looking into different type of hard disks and how what are their architectures. We will be looking at the different file systems as well. So mainly we will discuss the FAT file system as well the NTFS file systems. Then in the later half, we'll be discussing about window registry, what window registry is, what type of information it stores, and what can we retrieve from window registry. Then we'll be also be talking about some other topics such as the Microsoft Windows startups, like how the Windows starts up, what are the prefetch files, what is Slack space, and so on. So let's first talk about the hard drive architecture. Let's see what are the different type of architectures or what are the different type of hard drives. So mainly we have two different types of hard disks. First, we have the magnetic disks that are traditional disks that you see in your computers, and they are simply also called hard disk drives or HDDs. And another form of hard drives or another architecture is called solid state drives. So the solid state drives, these are in generally you can see them in your modern computers as well as other devices that we use generally these days. The way or the material with which these devices or these drives are made up of is also different. The HDDs use the magnetic material, whereas the solid state drives use flash memory chips in order to store the data. So this is how your traditional hard drive looks like. You have different disks, or they are also called platters. These are like metallic disks, and they are coated with magnetic material that you can change. So you can change their magnetic direction in order to save the data on top of them. So let's look into the architecture, or what are the different components of it. So the hard disk consists of different platters. So the disk type objects that you see here, these are the different platters on which you can store or you can write the data. All of these platters in a hard drive, they are like put on a spindle. So a spindle is just like a rod that moves and it rotates like the whole hard drive. The hard drive has like a magnetic surface on both sides. So the upper surface as well as the lower surface, you can write the data on both of them. And the hard drive also have heads, which are called read or write heads. So they have one for each disk or for each platter, you have one head in the top surface and one head at the bottom surface. So these heads, these are used to read or the write the data on each of these platters, and you see these headers both on top as well as the bottom surface on all the different platters that are there in your hard drive. Now, to further organize the data on one platter, it is further divided into different racks. So you can see one platter has multiple racks like this one. And this is also an illustration of different racks. So these tracks are the locations on the hard drive where you can store data. And these tracks, they are further divided into smaller units, which we call a sector. So a sector is a 512 byte region on one track on which you can store data. And this is the smallest unit in which you can store data. So if you are storing files, say 100 GBs or like say 100 MBs and so on, that file will be stored on these individual sectors, and each sector has 512 bytes in total. Uh, and this is also the smallest you can say unit in which the hard drive can store, read, or write the data. There is another terminology which is called clusters. So sometimes, not sometimes, like all the times, we combine one or more sectors together to form a cluster. So now what is a cluster? A cluster is the smallest unit in which our operating system is able to read or write a file. So these are the two different units. The hard drive, smallest unit is a sector. That's the amount of data a hard drive can read or write at any given time. But our operating systems, they have another different unit, which is called cluster. So whenever the operating system reads or write the data from any file, it will do so in the form of cluster. So it will say that this file is 3 clusters. So if one cluster is 5 sectors, you will have a total of 15 sectors on the hard drive representing that file. Another thing to another terminology is a cylinder. So a cylinder is a collection of all the tracks on all the different platters in your hard drive that are at the same distance from the center. So just assume like when we say this particular thing is a cluster, so it will have six different tracks, one from the top platter, top side one, bottom side two. Then we have two from here and two from here. So this cylinder, you can say it is the sixth track from the center or seventh track or nth track from the sector. So all of these tracks that are from the same distance from the center combined among all the platters, you combine them together and you will get a cylinder. So these are the different terminologies that we will be using, when we discuss the file system as well. So you need to know about all of them. So the next thing in the hard drives is the zone bit recording. So what is zone bit recording? To understand that, first we have to look at the different forms of hard drives. One, like the initial hard drive architecture and the modern hard drive architecture. So initially, like all these tracks in our hard drive, they were divided among different sectors. So you can see that this hard drive has multiple sector. This is one sector, this is second sector, third, fourth, fifth, sixth, and so on. Another thing in the older hard drives were that all of these tracks, for example, if a track is closer to circle, it will have the same amount of sectors as compared to a track that is at the edge or away from the circle. But just by looking at this image, we can see that the tracks that are near the circle or near the center, they are in smaller in size. So if there is like, if we just look at this internal track, if it is 512 MB, if we compare it to an outer track, a small portion of the outer track will have equal amount of data and the rest of the region will be wasted. So in order to avoid that, or in order to better utilize the our like physical space that we have on the platters, or the physical like region in which we can write data, we come up with something which is called zone bit recording, or ZBR. So what we did was we divided the whole hard drive, one platter, into different zones, and each zone has say four or five different tracks that are there in that particular zone. What we did was that we also changed the number of sectors that can be in one zone. So traditionally, all these tracks in the hard drive, they were considered as same, and they all had the same number of sectors. But now with the zone bit recording, what we did was we said that the tracks that are towards the center, since they are physically smaller in size, they have less number of sectors as compared to the tracks that are on the rim or that are outside. So from this picture, you can see that this zone, say zone 3, which is in orange color. So it consists of four or five different tracks. So all the tracks that are in one zone, they will have same number of sectors. So in this case, we have 1, 2, 3, 4, 5, 6, 7, and 8 tracks in the inner zone. As compared to this one, we have more than 8, like around 16 tracks in the outer surface or in the outer zone. So with this help of zone bit recording, the space that we were wasting in the older hard drives, where we had the same number of sectors in all of the tracks, we now have multiple tracks or different number of tracks for different number of sectors for the tracks that are outside, or for the tracks you can say that are like towards the edge of the platter. And we have some other things as well, such as track density and ideal density and so on. So track density is how many tracks are there in one particular, or how many tracks are there on one particular platter. So, like if you put more tracks, you have to squeeze them together. So there'll be less space between the tracks and there's more chance of data overlapping. Similarly, if you have tracks that are further from each other, then you will be wasting some space in between. Next, we have the other form of the hard drives, which are the solid state drives. And in solid state drives, we have like the controller that communicates with the operating system and file system. And you have the individual flash memories or NAND flash memory chips that are installed on your hard drive. So let's see the advantages or the difference between the two. So first is the latency. So the hard drives or HDDs, they are much higher, like, in size, as well as they take more as compared to the SSDs. Also, they are slower as compared to the SSDs because in the traditional hard drives, uh, we have to read or write the data, and there is a head that moves on platters, go to different sectors or different regions in the hard drive to read or write the data in there. As compared to that, in the solid state drives, we have, like since we have different chips, we can just like, store the data or read the data at a very fast pace. So they are high in speed, so and have less latency. You can do read or write the data at a much higher speed or in much less time. In terms of cost, since the hard drive, the modern hard drives or say SSDs, they are newer technology, they are more costly as compared to your traditional hard drives. And that's why you still see a lot of the traditional hard drives in the legacy systems, that it is very difficult and costly to replace them with the new solid state drives. Other things are like since the traditional hard drives, they are disks and they rotate and the head rotates. So there's a lot of rotation and movement going on in order to read the data. So that movement will produce, vibrations and sounds and so on. That's why if you see like, if you turn on your own old PC, you might still hear some, buzzing noise at the beginning or at the startup. And that is generally your hard disk like starting up when this platters start rotating in order to read or write the data, you hear those noises. Another thing is that these devices or the old hard drives, since they are all mechanical, if like you drop your PC or if there is like other disturbance or you can say internal force being applied, there is a chance that it will get destroyed faster as compared to the old SSDs. So here we just have chips, so no matter if there is like, any physical disturbance going on, the chips will not be damaged that quickly. So this is how the memory layout looks like on a solid state drive. So here you have the interface with which you will be communicating with the software or with the operating system. So this is your physical communication setup, physical SATA interface. Then each of the solid state drives, they have a SSD controller. So SSD controller is like a microprocessor that kind of manages all the read and write operations on the SSD, as well as communicating with the file system and the operating system. Then there are like multiple chips. These are NAND memory chips that are connected with the controller. And the SSD controller, whenever it receives, like any request to write a data, it finds the location or it finds some empty space in one of these NAND drives and then write the data over there. Similarly, if it is requested that data back or you have to read the data from these drives, it will just like, look at the address at which it stored the data last time, go to that NAND drive and then pull the data out from it and give it to the operating system or the file system. If we zoom in into individual NAND drives, then it consists of like there's a complete structure over there as well. So you can see like one NAND drive has multiple chips, and in one chip we have multiple platters or planes. So we have plane 1, 2, 3, 4 till n. Then we have further organization that each of these planes is further organized into different blocks, and the blocks are further organized into pages. So as compared to the HDD or like the traditional drive, where the smallest unit in which you can read or write data was your sector, in the SSDs, the smallest unit in which we can read or write the data is one page, and traditionally the one page is 4 KB in size, whereas one sector in the HDDs, they were 512 bytes. So now if you want to write some data, you can see the addressing. Like you will say chip number 1, plane number 0, block number 2, page number 1, and then write some data over there. And the SSD controller will keep a track or keep this location saved as well. Next time when the operating system wants to read this data, the controller will know that which location I need to look at in order to fetch that data back to the operating system. At the very core, if you look at one page, it consists of multiple floating gate flash memory cells. So you have different, like a lot of these hundreds and thousands of these small memory cells in which you can store data. So in the other drives, the HDDs, the data was stored in the form of like, on the like magnetic platters. So if you change their magnetic field of a platter at any given location, you can write zeros or ones. So for example, if you change the magnetic field to all toward north, it will be one. If you change it towards south, it will be zero. In SSDs, we have these individual cells that can store charge or that can store electric current. So if you want to write the data, you can charge this cell, it will be converted to one. And if you want to store zero, you can leave the cell without the charge. So in this way, all your data, whatever we see, like our sounds, our videos, images, programs, all of that, at the very end or at the bottom, it is all bytes, zeros and ones. So those zeros and ones can be stored in the form of charging and discharging some cells. So if you want to write, say, 1 byte, 100, 100, 100, so on, you can charge some cells and then you can leave the other cells without charge, leave them empty, then charge some cells again to represent ones. And in this way, you'll be able to store the data. Now, these cells, individual cells, once you charge them, the charge remain there because it has floating gates and top gates. So these two gates, they physically block the charge inside the cell. But no matter, like how many gates you put or whatever your technology is, technically speaking, these cells, they will discharge over time. So, like if you store data on a SSD, technically speaking, like maybe after say 100 years or something like that, that charge will be gone because these charge, they will be slowly, like decaying, or slowly the charge will be going out or getting out. So technically speaking, the SSD, maybe after one, I say, like a decade or 100 years, whatever data you wrote them, whatever charge you store in these cells, that will be gone, and the SSD will be all zeros. Another thing, or another, you can say, problem that comes with these SSDs or these memory cells is the memory cell wear. So what is that? The memory cell wear is that these individual cells, they can be charged, or to represent one, or you can discharge them to turn them to into zero. But this whole thing, like charging and discharging, there is a limited number of time in which you can do that. So traditionally, one cell can be charged or discharged maximum of 100,000 times. So if you read or write the data on one particular cell 100,000 times, after that, this cell will become unstable and you will not be able to write some data on it. This whole thing is called memory cell wear. And this is like a traditional, you can say, phenomena in all the batteries, like your mobile batteries or laptop batteries as well. They have limited age or charging cycle in which you can charge them and discharge them. And over the time, you can see, you might have seen that your mobile phone batteries or laptop batteries, their charging capacity decreases over time. They are unable to hold the charge anymore. So the same thing happens here as well. And this phenomena is called memory cell wear. So to reduce this, what is the effect of it? If you, for example, have a memory chip and you always use the first NAND drive, which is over here, to read or write the data, then you will be doing a lot of read-write operations on the NAND cell, on the memory cells in the first NAND flash drive or the flash chip, and the other NAND drives or the other flash chips, they will be unused. So if you are doing multiple read and writes on the same locations, over the time, they will become unstable and you will not be able to store data in them anymore. So your like memory space or the capability of the SSD to hold the data will decrease if you keep on reading or writing the data on the same location. So what we do to avoid that, some charges, like some cells or some blocks right here, they will go out or they will be destroyed after some times. They cannot hold the data anymore. So to avoid that, we have a wear level mechanism. So each of the hard drives in their firmwares, they have different algorithms that make sure that all the cells or all the blocks inside a SSD, they are used equally. And if they feel that some data is written on a cells, or you can say on blocks that have already been used a lot of times, and there is a probability that those cells will go bad, or like they will be damaged after some time, the hard drive or the SSD drive controller automatically, without telling the user, without telling the operating system, picks that data out from those like near death cells or near death blocks and put that data into some other blocks that are like more healthy and they are more capable of storing the charge. So this wear level mechanism is not governed by the user or the operating system. It is controlled by the hard disk itself. And this technology, or you can say these programs, they are installed in the firmware of the hard drive, and it happens in the background. Now, to like manage these bad blocks or these dying blocks of cells, there are different mechanisms in which we do that. The first is block replacement. So replacement and reverse block method, the simple idea is that the hard drive will have some blocks of data that are spare or that are separate, that can only be used when some of the existing blocks that are in use by the user go bad. So for example, if this in this particular SSD, you guys can see 6 different NAND drives or NAND flash memories. So the hard drive or the SSD will tell the user that it only has 5 working flash memories, and the sixth one will be labeled as spare memory or spare chip. So this thing, the spare memory or the spare chip, will not be advertised as available memory to the user. And from user's perspective, or say OS or file systems perspective, the max memory available will be just 5 chips. Now, if any of the existing cells in any of these 5 chips or any block is, damaged over time, then under those circumstances, the SSD controller will shift into reading and writing the data in the blocks that are in the spare memory, or then it will tap into the reserve blocks that were available there, not initially advertised to the user, but now the SSD will start using them. Another thing is called, now if like for some reason you run out of these reserve blocks as well, and there are no more healthy blocks that you can use, what will happen in if any block dies in that circumstances, then the hard disk will simply mark those blocks as bad blocks or bad sectors in the HDDs, and then try to avoid writing data in those bad blocks or bad sectors. So for example, just assume that over time we have been reading or writing a lot of data from this block to this particular location, like this whole addressing. Then over the time, it will become unstable. And if we don't have any reserve block, we will simply mark this block as unstable, and we will avoid reading and writing data from that block any further. So whatever data was there in that block, the SSD will automatically shift it to some other healthy block and mark this block as unstable or unavailable. So no further data can be written over here. So another thing or another phenomena, so this is wear leveling, or say, memory wear is one issue that comes with the SSDs. So whenever we are investigating with the SSDs, we have to make sure that, like we collect the data on time. And if we leave the data for a lot of time, there's a possibility that the SSD will discharge completely and the data will be wiped out. So this is only technically speaking can happen. In real life, it will take a lot of time. So another thing in the SSDs is that, another terminology which is called garbage collection. So let's look into that. So just imagine this is your whole SSD. So the operating system sees that there are a lot of different blocks in the SSDs in which I can write the data. So just imagine after some time, the OS wrote some files or wrote some data on the SSD. Some of these blocks will be filled, and after some time, after using or a file, you just delete a file. So what happens when you delete a file? The operating system will issue a trim command to the SSD, and it will tell the SSD that these particular blocks, whatever data or whatever file I wrote here, now I am deleting it, and these blocks, they are like free to use. You can wipe out the data that was in there. So the operating system, after when it receives or when it gives the trim command, the SSD will, this is how the table will look like. The different blocks in the SSD will look like. Once you delete the data, the SSD will mark those blocks as invalid blocks. And the SSD has a mechanism already built in, which is called garbage collections. So since these blocks, they are invalid now, they are not in use anymore. So whatever data was there is not in use anymore, and we need to delete it or wipe it out in order to make these blocks available for writing data again. So the SSD has another program running in the background, which is called garbage collector. So once the blocks are marked invalid by the operating system, or once you delete a file, whatever blocks were allocated to that particular file, they will be marked invalid. And the garbage collector, whenever this runs, so the garbage collector will be will run periodically in the hard disk SSD without the like interference from the user. So say like it is the frequency will be set by the manufacturer of the hard disk. So the SSD drive. So maybe they set it that, like run the garbage collector after every hour, or run the garbage collector after, every 6 hours or so on. So whenever the garbage collector runs, whatever blocks of memory that are marked invalid, the data in those blocks will be wiped out, and those blocks will be available for the OS again. They will be marked free again, and the user can write data in them. Now, what are the implications of this whole thing, or what is the forensic meaning of this whole thing? So if you look in the traditional hard drives or the HDDs, there is no such thing as, like trim, or no such thing as garbage collection. So even if the user deletes the file, the operating system deletes the file, the data still stays there. So even if, some blocks or some sectors in the traditional SSD will be marked invalid, or say, like the data in them will not be useful anymore, but the state that data will still stay there unless some other file updates that region of the traditional hard drive. But in SSD, since we have the trim command, and like this garbage collection running in the background periodically, so if you delete a file, it is possible that that file will be wiped out from your hard drive permanently. So in the traditional drives, even if we delete a file, we still have the capability of retrieving that file from the hard drive, because the data will be still be there. Only the pointers to that data or those sectors will be deleted. So you guys did this example too, or this activity too, in your lab too. You deleted some files, and then using the FTK imager and autopsy, you were able to restore the data or see the deleted data. But here in the SSD, if the data is deleted, and if garbage collector, whenever the garbage collection works or the program runs, all the deleted files, they will be like permanently deleted or wiped out from the memory. So now what are the implication of this thing? So in SSDs, for example, if you are, investigating a case and the user is using SSD, so you should try to collect the data as soon as possible, because if the garbage collection is running in the backend or in the background, that will be running because it is not controlled by the user. It is controlled by the SSD firmware. So whenever the garbage collection runs, it will wipe out the data. So as forensic investigator, our responsibility or our task will be to collect the data from an SSD as soon as possible, so that the deleted files, they are still in the hard drive, and we would be able to recover them. If the garbage collection runs, then whatever data was there, whatever deleted data was there in the hard drive, that will be wiped out permanently. So that's one thing that you should do. Like whenever you are investigating a computer, if it has SSD, try to collect the data as soon as possible. So to summarize the whole thing, like the SSDs and the hard drives, so the hard drives, they are magnetic drives. They consist of different platters, magnetic disks, coated metal disc coated with magnetic material that you can use to store data. In the hard drive, in the SSDs, we have the NAND memory chips that can be used to read or write data. When a file is deleted by user, the data will still stay there forever in HDDs unless it is overwritten. But in SSDs, the file that or the data that is deleted by the user, there is a chance that it may be lost forever. So whenever if the garbage collection function runs, or if that program runs, it will wipe out the deleted files. So this is one thing. So like you have different mechanisms with which you can read or write the data. You have different latencies, different speeds in which you can read the write data. The units are different as well. In SSDs, the smallest unit is 1 sector. In HDDs, the smallest unit is 1 sector, whereas in solid state drives or SSDs, the smallest unit is 1 page that you can read or write. And in SSDs, we have garbage collection, which wipes out the deleted data periodically. In HDDs, we don't have any such thing.